Amazon is spending $200 billion on AI infrastructure this year alone. Microsoft, Google, Meta, Oracle. Combined, the five largest tech companies have committed over $600 billion to data centers in 2026. That is not a typo, and almost none of it can be turned on. Not because the buildings aren't built, not because the chips aren't there, because there is no power. Because the grid that was supposed to deliver the electricity to run these machines is stuck in a queue, a bureaucratic, regulatory, physical queue, that in some parts of the country stretches to 7 years. 7 years. A company breaking ground on a data center in Northern Virginia today will not have a confirmed grid connection until 2031. If they're already in the queue, the United States is attempting to build the infrastructure of the next industrial era on top of a power grid designed in the last one. And the grid is losing. This is not a story about AI, it's a story about concrete copper wire, permitting law, and the regulatory architecture that decides whether America leads the next decade or watches someone else do it. To understand why the grid can't keep up, you first have to understand how fast the demand is growing, and why that pace was impossible to predict even 5 years ago. In 2022, US data centers consumed around 17 gigawatts of power. By 2025, that figure had climbed to 31 gigawatts. Goldman Sachs projects it will hit 66 gigawatts in 2027, more than doubling in 2 years. For scale, a single large nuclear power plant generates about 1 gigawatt. The US needs the equivalent of 35 new nuclear plants worth of capacity added to the grid in roughly 24 months. The grid was not built for this. The American transmission system was engineered over decades for a world of slowly growing demand, predictable load patterns, and centralized generation. What AI infrastructure represents is a demand shock with no historical precedent, hundreds of megawatts, sometimes more than a gigawatt, arriving at a single location all at once with a timeline measured in months rather than decades. The geography of this problem matters too. Data centers don't distribute evenly across the country. They cluster where land is cheap, fiber is dense, and power is available. Northern Virginia alone is the largest data center market on Earth, and its grid is already saturated. Texas, the Mid-Atlantic, and the Pacific Northwest are the next pressure points, each facing their own version of the same collision between private investment speed and public infrastructure timelines. And this is not an abstract infrastructure problem, it is already affecting households. PJM, the grid operator covering 13 states and 65 million people, held a capacity auction for 2027 and 2028 delivery. It failed to clear the market for the first time in its history. That means the grid operator could not secure enough committed power to confidently serve projected demand. The consequence flows directly to ratepayers. Utilities have requested $31 billion in rate hikes across the country in 2025 alone, and Goldman Sachs estimates data center-driven demand will measurably push core inflation higher through 2028. The AI boom is already on your electricity bill, before most of the infrastructure that caused it has even been built. The money is there, the megawatts are not. Here is how the process actually works. Because this is where the bottleneck lives, and most coverage skips past it. When a data center developer wants to connect to the grid, they submit an interconnection request to the relevant grid operator. That operator, one of a patchwork of regional transmission organizations that divide the country between them, then begins a series of impact studies to determine what upgrades the existing grid needs to accommodate the new load. Those studies take months, sometimes years, and historically they were done sequentially, meaning each new application waited for the one in front of it to finish before its own study could begin. As of the end of 2025, over 2,060 gigawatts of generation and storage capacity were sitting in interconnection queues across the United States. That number exceeds the entire installed generating capacity of the American grid. The line to get on the grid is longer than the grid itself. Historically, most projects in that queue never get built. Lawrence Berkeley National Laboratory found that only 13% of capacity that submitted interconnection requests between 2000 and 2019 had actually reached commercial operation by 2024. The rest either withdrew or are still waiting. The median time from application to operation has more than doubled since 2000, from under 2 years to over 4. The queue is clogged not just by slow processing, but by speculative applications from projects that will never be built, holding a place in line and blocking the ones that will. It's worth pausing on that 13% figure because it understates how broken the system is. The projects that do make it through are disproportionately the ones with political support, patient capital, or grid operators in regions that have already implemented reform. The ones that withdraw are often the projects that ran out of time or money waiting for a study that kept getting pushed back every time another project ahead of them changed configuration. Restudies cascade through the queue. A single large project dropping out or redesigning can force reanalysis of every project behind it. But the queue is only part of the problem. Assume a project successfully navigates the interconnection process. It still needs physical infrastructure. And that infrastructure is made of things that take a very long time to manufacture. High-voltage transformers are the critical component connecting new generation or load to the transmission grid. Before 2020, lead times for a large power transformer were 24 to 30 months. Today they stretch to 5 years. Pre-2020, you could order one and have it delivered before your data center was finished. Today you need to place the order before you've broken ground, before you have a permit, sometimes before you have a site. The transformer needs to be on order before the business case is fully closed. This is not a quirk. It reflects a structural reality. The manufacturing base for grid-critical equipment was never scaled for a demand surge of this magnitude. There are only a handful of facilities in the world capable of producing the largest high-voltage transformers, and their order books are full for years. Unlike software, you cannot ship a patch. Unlike chips, you cannot fab a second foundry in 18 months. The physical components of the grid are built at a pace that reflects a different era's expectations about how fast the world would need to change. The regional picture makes this concrete. In Northern Virginia, Dominion Energy's interconnection queue now stretches to 7 years. PJM is managing a 140-gigawatt generation backlog, with 94% of projected new peak load growth through 2030 driven by data centers. In Texas, interconnection requests for large loads grew 700% in a single year between 2023 and 2024. And the transmission lines that would carry power from where it's generated to where it's consumed require their own separate permitting process, one that takes more than 10 years on average from start to finish. Site a transmission line today, and it will not be operational before 2036. The U.S. completed nearly 4,000 miles of new high-voltage lines in 2013 alone. Since then, the pace has fallen to a fraction of that. There are two separate crises here, and conflating them leads to bad policy responses. The first is regulatory. The interconnection queue process was designed for a different era. FERC's Order 2023 shifted to cluster-based processing and raised financial requirements to filter out speculative applications. Those reforms are still being implemented. What is measurable right now is that entering the PJM queue in 2026 means no interconnection agreement before 2028 at the earliest, under optimistic assumptions. Reform is happening, but on a timeline that does not match the urgency of the capital currently being deployed. The second crisis is physical and harder to solve with rulemaking. Consider what it actually takes to build a large transmission line in the United States today. A developer needs environmental review under the National Environmental Policy Act, citing approval from each state the line crosses, coordination with the Army Corps of Engineers if it touches a waterway, Bureau of Land Management review if it crosses federal land. Each of these processes runs on its own timeline, with its own comment periods, its own litigation risk, and its own opportunity for delay. There is no single federal authority that can say yes and make it happen. That fragmentation was designed to protect landowners and ecosystems. It was not designed for a world where the grid needs to double in a decade. This is the fundamental mismatch. The most capital-intensive private build-out in American history is colliding with a public infrastructure system built for a world that no longer exists. Step back from the interconnection queue, and what you're looking at is a question about American industrial competitiveness in a domain where the stakes are not abstract. AI infrastructure concentrates where power is cheap, available, and fast to connect. Right now, that advantage sits with the United States, but it is not structural. China is building data center and transmission infrastructure under a centralized system with no 7-year interconnection queue and no requirement to coordinate permitting across a patchwork of independent state regulators. The EU is building under explicit industrial policy with grid expansion targets written into law. The US is building under a regulatory framework whose foundational architecture dates to the 1930s. The historical analogy worth paying attention to is not another country's grid, it's America's own semiconductor industry. The US spent decades as the dominant producer of chips, Gradual offshoring, driven by cost optimization and the assumption that production location didn't matter. Transferred manufacturing capability to Asia. When the supply chain broke in 2020 and 2021, the US discovered it no longer had the domestic capacity to respond. The CHIPS Act is the multi-year, multi-billion-dollar attempt to rebuild what was given away. The question now is whether the US is making the same category of mistake with energy infrastructure, allowing the permitting system to function as a slow-motion transfer of competitive advantage to countries willing to build faster. The concrete version of losing this race is not dramatic. It doesn't look like a sudden collapse. It looks like data centers that get built in Canada or Mexico instead of Texas because interconnection timelines are shorter. It looks like hyperscalers shifting investment to regions where permitting moves faster. It looks like the US remaining a major player in AI software while quietly ceding the physical infrastructure layer, the grids, the factories, the supply chains, to countries that built the institutional capacity to move at the speed the moment requires. The companies betting on American AI leadership are already hedging the risk. Oracle is building data centers with on-site natural gas generation that bypasses the grid entirely. CleanView estimates 30% of new data center capacity in 2026 will come from behind-the-meter generation, up from nearly zero a year ago. The private sector is building a parallel energy infrastructure, campus by campus, that routes around the public grid rather than waiting for it. It's worth being precise about what this argument is and isn't. This is not an argument that the AI build-out will fail. The hyperscalers have the capital to route around the grid, build their own generation, and absorb delays that would bankrupt smaller players. What the bottleneck does is raise costs, extend timelines, and, most importantly, make US infrastructure less competitive relative to systems that can move faster. The reforms underway at FERC, the permitting efforts at DOE, the supply chain investments in transformer manufacturing, these are real and they matter. The question is whether they are moving fast enough, and whether the political will exists to sustain them through the years it takes for infrastructure timescales to compress. So here is where things stand. The United States is attempting the largest industrial build-out in its history, $600 billion in a single year, aimed at cementing dominance in the technology that will define the next several decades. That build-out depends on a power grid that takes 7 years to connect a new customer in some regions, 10 years to permit a new line, and 5 years to manufacture the transformer needed to do either. The capital is moving at the speed of software. The infrastructure is moving at the speed of concrete. That gap is not a technical problem. It is a governance problem. A question of whether the United States can coordinate permitting, manufacturing, planning, and investment at a pace that matches private ambition. The countries that solve it first will host the infrastructure of the AI era. The ones that don't will import the output. America has done this before. The interstate highway system, rural electrification, the interstate natural gas network, each required building public institutional capacity alongside private infrastructure. The question is not whether it's possible. The question is whether it starts fast enough to matter.